So, okay, we will continue. Okay. So, in the last class we were trying to understand that, right, how absorption bands comes into picture. So, this absorption bands corresponds to, in our case when we are working with photonics, means corresponding to either UV or visible range or near infrared range photons, right, wavelength range photons gets absorbed and then they induce, right, either vibrations or right, atomic transitions, etc., right. So, if it is at a molecular level, it can be exciting to the electronic transition from ground level to the excited electronic state, or within the electronic transitions there are rotational transitions, vibrational transitions. Vibrational transitions are right, they result in let us say absorption in the visible range or near infrared range, near infrared, mid infrared range, while rotational transitions go to mid infrared to near infrared range. Okay. Very small transitions, certainly the wavelength order will be longer, right, and when it is electronic transitions, it is in UV range mostly, or right, different frequency bands depending upon the molecular structures, we will have different frequency bands, as well as there are certain rules, right, for the transitions, and they are being followed, which will determine the corresponding energy transitions. Now, each of these transitions have certain strength, or basically what is such probability? You can say something like transition strength, which is represented by sigma 1 to absorbs, right, Einstein's coefficient, and that Einstein's coefficient which is B12, right, is indirectly determines the line strength or the transition strength, okay, and correspondingly the probability of transition is, right, determined. So, if the incoming photon is there, what is that? Basically indirectly it represents the probability of that photon getting absorbed, and the right, a molecular structure get excited. Now, all these transitions depending upon their right energy band gap, etc. So, there will be there will be multiple, right, within the vibration bands there will be lots of rotational bands, and each of these vibrational band transitions right, depending upon their energy levels, etc., will, and depending upon many such energy levels vibrational transition bands, a molecular structure may have such right transitions. So, this is let us say molecular structure of hydrochloric, right, HCl, right, in a gaseous state, you will see that there are many such transitions, and all these transitions, the shorter wavelength transitions are related to P, right, transitions. Then if it is a symmetric structure, we will end up with a Q band which is 0, and then R bands. Okay. Now, some of the symmetric structures with various such transitions are shown like this. Now, x axis is, it can be frequency, it can be wavelength, or it can be wave number, centimeter inverse, correct. That is what, so we realize, while y axis represents the transition strength, and it can be absorption cross section value. Okay. So, let us say for this is about CO2, okay, carbon dioxide, right, molecules. Carbon dioxide molecules in 1.6 micrometer wavelength range has multiple such transitions, okay, and it is something like a finger like structure, right, left and right and left hand, and these transitions are because of there are various molecular state vibrations, the combinations overtones of fundamental frequency 2 nu 1 plus 2 nu 2 plus nu 3 provides such transition. Of course, the fundamental transitions will have a very large absorption cross section value, probability will be large, but because of such transitions and combinations of all these transitions, we may also end up with absorption bands in such combinations, combinatorial or combinational transitions. Okay. So, if we consider let us say methane, methane has like this nu 3 is one of the vibrational band, and the second harmonic or second overtone of that methane is in 1.6 micrometer range. CO2 I already told you, H2S hydrogen sulfide has such transition absorption bands. Y axis is absorption cross section. Of course, when all this various such transitions depending upon different gaseous molecules have been derived by various research groups, okay, in physics, chemistry, everyone, and there is a database available, heat-run database, which is being updated since 1960s, 70s, it is being updated. That database gives us what are those bands. This is just I have taken just to give you an idea that depending upon what molecules we are looking for, let us say if this is CO2, this is a CO2 band. So, at different frequencies they have different such absorption bands. Okay. Absorption cross sectional values may be different, okay, depending upon the band vibrations and band transition strains, etc. So, if we are considering let us say NOx, so NOx has NO has such absorption bands. If we are considering let us say methane, then methane has like this, different such transition bands available, absorption bands. We can make use of such absorption bands in order to derive some some quantitative information, okay, and that is based on absorption spectroscopy. So, how this absorption spectroscopy works already initially when we were discussing we have talked about it, but once again. So, basically let us say any medium, let us say it is a molecular a medium, liquid or gaseous medium, and when light transmits through this with a particular wavelength, correct. Now, you must understand that this wavelength what we describe has some important information hidden, the corresponding to this wavelength, and for a particular let us say molecular, let us say it is CO2 has a certain absorption band, and so this wavelength is selected based on matching with the absorption of CO2 molecules, and corresponding to this wavelength and the CO2 molecular database, we know what is the absorption cross section. Okay. What it means, when the light of a particular power with a certain cross sectional area strikes interacts with those molecules, some part of that light will get absorbed by the molecules, okay. And what is it is represented by absorption cross section of the molecules, which is the line strength of this absorption is represented by absorption cross section of molecules, and it is represented by sigma. Now, as I told you and as you could see in the previous plots, different molecular structures, different wavelength bands have different such sigma value. Depending upon what wavelength I select, correspondingly there is a absorption cross section value available from the database. So, sigma value is determined based on the what wavelength we use, and when light passes through this structure, let us say gas cell of length L, part of this light is getting absorbed, right, it is getting absorbed. So, the transmitted light intensity is this, and based on the Beer-Lambert's law, transmitted light intensity is 0 exponent of minus sigma lambda into n into L. Now, this n is nothing but the concentration of the molecular species what we are, right, concentration. Okay. So, concentration of the molecular species. Okay. Assuming we are just talking about only one molecular species, okay, and corresponding to that we are, right, and L stands for the length of the this gas cell. Okay. Now, sigma is absorption cross section, it is generally its units are, let us say, centimeter square. Okay. And concentration is number of molecules numbers per centimeter cube. Okay. And sigma into n, sigma this lambda into n is known as absorption coefficient. Okay. Okay. And this is represented by alpha, and this alpha value, okay, is of course based on the units, it is per centimeter, right, centimeter inverse. Okay. That is. Now, how this alpha value is derived? Basically, this alpha value depends upon the absorption, okay, and concentration, of course, right. So, for a given concentration, as the sigma lambda varies, accordingly alpha will vary. Now, this sigma lambda is nothing but the absorption cross section. So, basically at a resonance where absorption is dominant, okay, at a particular frequency where transition takes place, molecular transition, there is a, it corresponds to the resonance, it corresponds to the absorption, right, and that is connected with this alpha value. Okay. I am not going into details of this molecular right absorption and transition, but I will just give you a hint. So, if you go back, or I will also upload some written material, and you will understand how this absorption comes into picture. Okay. So, basically it is something like let us say this is nucleus, okay, nucleus, right, atomic structure as a nucleus, and electrons are connected through, okay, I am sorry. So, it is this is, let us say, electron, okay, and this is nucleus, right, which is certainly very heavy. So, it is acting as a mass, correct, and this is spring, and it is connected to the nucleus with spring and damper this electron. Okay. So, when electromagnetic wave comes, okay, with a frequency h nu, okay, right, what will happen? Corresponding to the electrical field oscillations with a frequency nu of this electromagnetic wave, this electron will start oscillating. So, it is a forced oscillation, it starts, correct. So, if we can use mass spring damper, right, system, right, damper system, and derive the governing equation for this forced oscillations, correct. The forced oscillation is due to the electrical field, right, into charge, which is nothing but the electron, right, over here is inducing a forced oscillation, and this oscillations will end up with the frequency matching with, in a linear right. If we think whatever is the induced electrical field, right, frequency, accordingly the electrons will also start oscillating with this. And if we use this mass spring damper approach in a very simplified way, we will be able to derive the resonating frequency corresponding to the spring and this, right, coefficient of damper, right, etc. We will be able to derive when is this electron going to have what type of resonating frequency, and spring constant and this damping coefficient depends upon energy levels, energy structures. Based on that, the particular electron will have a particular type of spring, right, a constant and electron, and accordingly this is of course atomic level I am explaining you. It's there is no, right, molecular part, it is only nucleus and electron, just a very simplified model, but it will give us the resonating frequencies, and those frequency corresponds to the absorption band. And you if we go into little detail, we will be able to see that if this electromagnetic wave with a frequency h with nu as the frequency interacts with such spring mass damper, and if the resonating frequency of this spring mass damper electron connected with nucleus matches with this incoming electromagnetic wave, right, frequency, then electron will start oscillating, it will be in a resonating condition, absorption comes into picture, and the transmitted light will right, experience this absorption. Okay. So, the electromagnetic wave which in turn will result due to this electron vibrations, and which is nothing but the transmitted intensity, right, electrical field will be something like E transmitted will be E0 exponent of, right, some constant, let's okay, let's say I don't want to put alpha because it may be the previous alpha may be different. So, okay, maybe we will say something else. Okay, what I have put, let us say alpha absorbs, okay, to x. Okay, so this is this parameter means the electromagnetic wave and transmitted through this medium, and electron starts resonating corresponding to the input frequency, and then the transmitted electrical field will be like this. So, this we will be able to derive, okay, based on this model, and this parameter has a relationship with the what I am explaining I intensity, of course not the electrical field, I transmitted, right, corresponding to I is 0. This is exponent of minus of 2, why minus, you know, because electrical intensity of electromagnetic wave is proportional to E square, right, E square we know, right. So, it will be like this. So, this parameter is nothing but the alpha what I, right, I described over here. Oh, okay, not here, maybe here. Okay, we wrote, no, where is it? It and I is equal to Beer, right, Johnson Beer, okay, Beer, this is Beer-Lambert's equation, right, Beer-Lambert's equation is that alpha is nothing but this alpha, and if I use, okay, 2 level energy system N1 and 2 with, right, h nu, and let us say number of photons are n, whatever number of photons comes, I consider absorption, okay, spontaneous emission, stimulated emission, all these parameters, and derive the relationship between this incoming photons, then transitions and outgoing photons. If I derive the relationship from here, okay, also I will be able to derive intensity, the light which is passing through. Okay. And if I compare this right with the previous this equation, okay, I will be able to know the relationship between alpha and sigma and concentration. Okay. If the n concentration here n represents the ground level concentration, okay, assuming the upper level population is very small, generally Boles right when we use Boltzmann right thermal equilibrium, the upper level population is generally neglected, it is very small. So, we can neglect ground level is right largely populated, much more populated. So, although it n is nothing but actually n 1 minus n 2, right, but we neglect n 2 and we just consider the ground level population. So, ground level number of atoms or number of molecular right transients. So, that corresponds to alpha is related to sigma and n, sigma is derived from this part, alpha is based on the previous our electromagnetic waveform, right, and n is number of such ground level atoms, right, they have this relationship, alpha is nothing but sigma into n 1 minus n 2 or n where we neglect n 2. Okay, we do not consider. So, basically what I am trying to say that this sigma into n and into the length through which it is passing through based on the intensity measurement, we will be able to derive absorption, right, or concentration means as why I am okay, yeah, it was here, no. So, if I know input intensity from the wavelength of the light which I am using and from the database I would be knowing what is sigma value, I would be and if I can measure transmitted intensity, and if I know the length of the gas cell through which the light is getting transmitted, I will be able to, I know this IT0, I know I0 lambda of course, right, lambda, okay, I know sigma lambda, I know L, I can derive the value of n. 1 minute, here this you understood, no, this lambda, sorry, not alpha, lambda, no, alpha value. Now, this is known as here this is absorption coefficient. However, in some cases there will be scattering. Okay. So, what slightly complex part, one more extra step, not very complex in the sense that let us say I am considering a transmission of the light I 0 lambda getting transmitted, it is I t lambda. Okay. And what previous equation what I had mentioned is if this is length L and if there are some molecules which are CO2 molecules, let us say it has a certain absorption, right, cross section. So, corresponding to this lambda and corresponding to this molecular structure, we know what is sigma lambda value. So, from this, as I had written in the previous equation, I can easily find out the concentration, correct, is what I mentioned in the previous case by using this form, okay, where sigma lambda into n is known as absorption coefficient. Okay. Okay. Now, okay, these are the particles, okay, which are CO2 particles. Now, you consider some scattering medium along with CO2, let us say there are some other particles, okay. They are not absorbing the light, but they are scattering the light. Okay. So, the transmitted light intensity I t lambda, right, will not be now same as only what was observed only in the case of CO2 molecule, correct. So, what you will get is some other value of lambda, right. Now, this lambda IT lambda, now it is this transmitted intensity right is based on scattering due to the light input light interacting with this scattering particle. So, some light is getting scattered, okay, and absorption due to CO2 molecules. Okay. So, the transmitted intensity I t lambda will be equal to I 0 lambda into exponent of minus now sigma of a scattering medium, okay, and concentration of scattering medium, okay, which of course I do not know, okay, let us assume, okay, just to simplify at present. So, let us say instead of sigma I will write alpha of scattering medium, okay, into L is absorption due to scattering medium, okay, plus alpha of absorption medium, which is CO2 in this case. Okay. So, maybe I will write in terms of alpha CO2, correct, alpha into concentration of CO2, is not it? Sorry, alpha contains N. So, there is no need of this constant. So, this into L, correct, same L. So, if I take out L as common factor, so what will happen? This can be represented by alpha scattering plus alpha absorption due to CO2 molecules, right, into L, correct. And this can be, this is nothing but attenuation coefficient, right, it is getting attenuated. See, if you do not know molecular CO2 concentration, you do not know scattering also concentration, what you are going to measure? Input intensity, transmitted intensity, correct. You know the length through which it is transmitted, you can derive alpha, right. I transmitted with another color. So, I transmitted is into alpha attenuation into L, correct. This will be the formula, right. I will not be knowing N in any case anything, I will only know input transmitted input intensity length, whatever I derive is a combination of scattering, absorption, etc., etc. So, that is attenuation, is it okay? Little more, if there are let us say two different gas molecules, okay. So, there are different gas molecules, okay, combination of this, right. And so, now input is I 0 lambda, transmitted I t lambda, length is L, and both of these molecules, okay, let us say this is molecule, right, for CO2, let us assume this is molecule for water vapor, let us say vapor, okay, water vapor, okay. Both of them are absorbing this incoming light, right. I do not know the concentration of water vapor NH2O, I do not know concentration of CO2, but I know sigma of CO2, right, at this wavelength I know from the database. For water vapor also I know sigma for water vapor also from the database. So, overall transmitted intensity is a combination of exponent of minus sigma of CO2 corresponding to the wavelength lambda into concentration of CO2 plus sigma of H2O corresponding to the wavelength lambda into concentration of H2O, right, will into L will be the case, is not it, transmitted. Is it okay, Basa? Is it fine? And if I consider even scattering on the top of this, so it will become this formulation will be slightly different. So, it will be okay, maybe I will remove this. So, over and above there is scattering. So, into let us say alpha scattering to L, correct. Some scattering may also happen. So, there will be aerosol particles, right, which may also scatter the light, okay. They may also scatter the light, is not it. All this combinations will result into some, right, transmission absorption. To differentiate this values, okay, what shall we do now? Let us say we will not consider scattering, okay, we will at present we will assume there is no scattering, it is only there are two molecules, okay, CO2, okay, CO2 molecules and water vapor, only two molecules, okay, which are absorbing incoming light. And so, in this case our formulation, if you see the previous one, transmitted light is equal to input at a particular wavelength exponent of minus sigma of CO2 corresponding to lambda to n of CO2 plus sigma of H2O vapor, water vapor, of course vapor, into concentration of water vapor, correct. This will be the formulation. Now, if I want to derive both concentration of CO2 and concentration of H2O, what shall I do? I should use two different wavelengths, because there are of course simultaneous equation, no, there are two unknowns, right, there are two unknowns, these are the two unknowns. So, there will be there should be two equations, and two equations means two different wavelengths will use and derive the value, right, easily. So, two different wavelengths can be various combinations, means I can select a particular wavelength matching with CO2 absorption, but there is no water vapor absorption. I can find out from the database, correct, and I can select that wavelength, then automatically this equation becomes much more simplified. I need not worry about water vapor, and I just worry about the absorption by CO2. Of course, there will be some scattering due to water vapor, right, I will have to be careful, but I can derive, okay, some value. And another wavelength I can find out, which where there is no CO2 absorption, only water vapor absorption, and I can derive water vapor concentration, or I can take another wavelength which has both CO2 and water vapor. From the first wavelength I have derived the CO2 concentration, I can substitute here, and for the another next wavelength I can derive this, okay. All I can decide, it is a differential absorption, right, you differentiate between these two, right, this part, right, with so if there are multiple molecules, if there are 3 molecules, mixture of various molecules, there will be mixture of, means different wavelengths I may have to use, right, or selectively find out each of this wavelength, correct. And another aspect related to scattering, okay, scattering comes into picture, right. Now, if I am selecting, let us say over and above, now there is a scattering also coming into picture, okay. So, plus here there is an L, sorry, here there is L. So, plus we are writing scattering also, okay, alpha scattering, okay. Now the thing is, of course, I can select two wavelengths, right, and try to derive this part, but then scattering is common in both the cases, is not it. So, the idea is our over and above scattering coefficient also depends upon wavelength. Okay. So, if wavelength changes, the scattering coefficient also changes. Okay. So, either I should select 3 different wavelengths and then try to derive this values etc. Other way round is I can take of course 3 different wavelengths, but very nearer to each other, very nearer to each other. Okay. So that the scattering coefficient remains constant parameter. Okay. It will not change. See, with wavelength change scattering coefficient changes, but not as fast as the absorption parameters. Okay. So, over a certain wavelength range alpha scattering may be approximately constant. Okay. So, I can select that particular range of alpha value and try to see that the scattering is constant. Okay. Then I can easily eliminate it, right, without knowing the influence of wavelength on scattering part, right. I will assume it is almost constant, because wavelengths which I selected for absorption of CO2, water vapor etc., are nearby, and so the scattering is almost constant, same for all the cases, okay, for both the cases, that is why. Okay. So, all these ideas are possible to explore. Okay. Now, before we go to something related to such trace gauge sensing etc., one simplest example of this absorption in our photonics, right, area is nothing but a blood sample, right. So, blood analyzers, oxyhemoglobin measurements etc., are based on this absorption spectroscopy technique. Okay. It is very easy to derive. So, pulse oximetry is also based on this spectroscopy technique, absorption spectroscopy technique. So, we try to select wavelengths corresponding to, now I am interested in measuring some absorption species. So, I will try to select a particular wavelength and corresponding to that what is the absorption. If I know, I will be able to measure approximately, I can derive the concentration, is the idea. Okay. So, in this spectrum I had shown to you previously also, we are interested in the blood part, right, blood, oh okay, right, blood this. So, this part is right very clear, right, you now know, okay, whatever I described in the previous case is this. Secondly, just for your reference, okay, it's not it's available everywhere, but remember, okay, because when I talk about number of molecules, some textbooks will write in terms of number of moles, and sometimes they may also, in case of liquid, it will be moles per liter etc. Okay. So, you may have to use some simple mathematics to derive the values. Okay. So, I just wrote it down, number of moles corresponds to number of molecules divided by Avogadro number, and what number of moles represent? Basically, if x number of moles are there, that means if we know the molecular weight, we can also derive the mass of that. So, okay, molar mass of okay, and gaseous molecules, of course, we do not very much, because 1 mole corresponds to how many liters at STP, standard temperature, normal temperature and pressure, it is 22.4 liters, right, this. But in aqueous solution, it is represented by molarity. So, number of moles divided by volume in liter, okay, what we measuring volume will give you the molarity. Okay. So, these are some terminologies, okay, just for your reference, it's you may be knowing about it, because many of the textbooks they will give values either in terms of moles per liter, millimole per liter etc. So, the previous right will help you. So, as I told you, in case of blood we will try to measure partial pressure of oxygen or CO2 etc. and the recently with pulse oximetry saturation, right, oxygen saturation we try to measure. We do not measure partial pressure of oxygen or so, because it is not very easy to measure oxygen. Partial pressure of oxygen means what, within that blood gaseous right things if we consider in the blood plasma, right, and if we derive the oxygen which is in terms of how many number of molecules of oxygen, right, within. So, from there we can derive the partial pressure etc., but then it depends upon temperature and various other parameters. So, generally it is not easy immediately to get the answer, rather saturation or pulse oximetry approach is very easy to derive how many number of oxygen molecules are attached to the hemoglobin, gives us some approach, okay, of equivalent measurements. The things may be slightly different, but equivalent measurements we get. Similarly, electrolytes also, there may be some interest in measuring electrolytes and sometimes metabolites such as glucose or right lactate or right, all such will depend upon how many milligrams per milliliter, and if you know the molecular weight etc., you can derive how many moles etc., right, from there. Now, in this plot x axis is partial pressure of oxygen. I am trying to now give you the idea how oxygen saturation is connected with right, it is connected with partial pressure of oxygen present in blood. Okay. Now, generally when the partial pressure of oxygen is around 12 to 14 kilopascal, we will reach approximately 100 approximately right 98% of saturation of hemoglobin. So, hemoglobin will if right will oxygen will get connected to the hemoglobin, oxyhemoglobin will be formed. Okay. So, if the oxygen percentage right or oxygen partial pressure of oxygen decreases, that means amount of oxygen in blood decreases, correspondingly the oxygen getting attached to the hemoglobin will decrease, and we see that below right 10 or 8 partial pressure of oxygen, the oxyhemoglobin level decreases exponentially down. Okay. And that is why you must have heard during right pulse oximetry below 80% it is very danger limit, because even a small decrease in oxygen level will end up with a very small amount of oxygen coupled with the hemoglobin. That means, oxygen reaching to the tissues will decrease enormously. Okay, will change this. So, pulse oximetry and other approaches generally is very simple, and they try to measure saturation. Okay, and from saturation indirectly it is assumed that okay, if the saturation is 95-98% approximately, that corresponds to this much amount of oxygen present in blood. Okay. Now, so this is just to give you an idea. Now, what is this oxygen saturation? It is amount of oxyhemoglobin divided by total hemoglobin. Okay, total hemoglobin, which is reduced hemoglobin right plus oxyhemoglobin is the total hemoglobin. Okay, that is. Okay, so now, if you see the hemoglobin spectra right absorption spectra and oxyhemoglobin absorption spectra, it is something like this. Okay. This is x axis is wavelength, and what you are seeing here is around 650 nanometer or so, maybe here right around this wavelength. You see that there is a large difference between hemoglobin and oxyhemoglobin. Okay. Around 800 right nanometer or so, which is isosebastic right point. Basically, what it means is the absorption values are almost the same. okay, oxyhemoglobin and hemoglobin, and around 920 940 nanometer, right, it is other way around, right. So, oxyhemoglobin absorbs more light, attenuation, extinction, right, is large, and right, for oxyhemoglobin, while in visible range 650 nanometer, hemoglobin will absorb this light, okay. So this basically an indicator of indirectly it is an using this wavelengths, we should be able to derive the information about presence of oxyhemoglobin and hemoglobin, right, because as we can see that if I use light at this wavelength 660 nanometer, right, I will not consider scattering etc., I just consider absorption by these two molecules only. So, intensity of the light, transmitted intensity of the light will depend upon absorption coefficient of hemoglobin and oxyhemoglobin, is not it. And so, and here it is other way around, right. So, two wavelengths I use and I can derive both this concentration values. Time wise, okay. Tomorrow we will see how these two wavelengths, and then tomorrow we will extend, I will give you some hint about this measurement approach, then we will extend it for same absorption analysis for maybe glucose measurement, metabolites, or even human breath, right, measurements etc. How can we do that, okay. So, thank you very much.